So now I want to talk about equilibrium and free body diagrams. So again, we always are starting with free body diagrams before we move on to the calculations, since drawing your free body diagrams is really where you do the physics. So there are three things to think about when you have an equilibrium situation. First is that you should have no net force in your x-hat direction. So if you sum up all of the forces, specifically their x components, you should get 0. Similarly, you should have 0 net force in the y direction. You sum up their y components, you get 0. Now, in this first case, this is simple in that you don't actually have any forces in the x direction. So if I wanted to sum up what's happening in the y direction, I would say that the sum of my y forces equals my tension force, which note that my tension force is in the positive y direction, so I can write this as positive t y hat. So I've given it a magnitude, which is positive t, and, well, technically t is the magnitude, positive y hat's the direction. Now if I come down here and look at gravity, this is going to be equal to negative. Now in this case I'm still calling it FG, we're not worried about what that's equal to yet. Y hat, it's in the negative direction. So if I come up to my forces in my y direction, I have positive t. I'm not going to worry about the direction. I'm only thinking about the components now. So this becomes a one-dimensional problem. I do need to worry about signs, but I don't need to write the directions themselves. So then this is positive t minus fg. Now, because this says that f net equals 0 and the vector symbols are here, this means that each component must be equal to 0. So here we would say this equals 0. From this, what do we know? Well, for this situation, we would see that tension then must equal Fg. Note that in this case, these are the magnitudes, and you would come back here to see that yes, these forces are equal strength, but opposite direction. So please be very careful about your directions. I recommend always writing that out explicitly as a positive or a minus. So that's what's happening here. Nice and simple. This would, for instance, be a brick that is hanging from a rope and it is moving at a constant speed. The tension and gravity cancel out, so it's in equilibrium. It's still allowed to be moving. Now, in this case, you have the same thing happening in x and in y, in that you have two forces that are purely in y, two forces that are purely in x, and you can see that the thrust force and the drag force are equal in opposite directions, equal magnitudes, same for the normal force and the gravitational force. Now what I want to highlight is that you might need to find a missing force, and that's something that's going to come up a lot in equilibrium. That you might, for instance, be given part of your situation and need to identify the direction and size of the force. So what might this look like? Well, imagine that you didn't know that the drag force was there, and you only had what was remaining of the free body diagram. If you were told that this object had a thrust force forwards, imagine, for instance, a jet airplane, and on the ground that is moving forwards at a constant speed. You know that you have the normal force, that's why I said this was a jet on the ground, and you have the gravitational force, but if you're told that the net force equals 0, the only way that this can possibly be true is if you have a force that is equal in magnitude but opposite in direction, and we would draw that over here. And obviously that is what the drag force was underneath my blue scribbling. So you won't always be doing that qualitatively by moving arrows around on paper. You're frequently going to be doing that mathematically, but understanding what's happening qualitatively with arrows is always going to be the first step. I'm now going to set up a problem. Again, I'm not going to do it in full detail since that would take a very long time, but I want to show you this situation. There's a beam, this wooden beam, that is supported by two ropes. So this would be effectively the sketch of your situation. Now, if it is not accelerating, right, it's just hanging there from the ceiling, we know that it's in equilibrium. We can say that F net is equal to 0, and it's a vector, because it's hanging there, it's at rest. So the first step is going to be to draw our free body diagram. I've started by drawing my beam as a particle. We don't care about its size or shape. That's again part of our force model, is simplifying it down to a particle. And I've drawn my coordinate axes. And there's a specific reason why I've chosen to do them this way. I am going to switch colors for my forces though, and that's fairly important. So now I need to identify what forces act on my object. I circle my object. And I want to highlight that my object is not the beam plus the ropes. This is my object. It is just the beam. So then when we say what forces are there, well, I know that there's gravity because it's on Earth, and I see that there's two tension forces. I'm going to call this tension 1, and I'm going to call this tension 2. Two ropes, two separate tensions. So again, be careful about that initial step where you keep track of all of this. So now I'm going to draw my forces up here. So I know that gravity, it acts down as normal. So this is my gravitational force. Now I have my two tensions. Now what I'm going to try to carefully draw is their angle, which is going to be a little bit difficult to do. And I want to think a little bit about my net force when I'm drawing these. So we can say that F net equals 0 since it's at rest, it's in equilibrium. What that means is the y components of my two tensions are going to need to equal gravity. So I shouldn't draw my tensions bigger in magnitude than gravity. Next, I know my x components of tensions are going to need to be equal. So the two tensions might actually be a little bit different. Now, again, drawing this is something that you might not do it correctly until you do the calculation and see this. It is okay to go back and correct your free body diagram, but it's important to realize that if you draw your free body diagram incorrectly, that you might be leading yourself to do the physics also incorrectly. So I am going to draw tension 2 up this way, tension 2, and tension 1 is going to be up this way. And it's hard to actually do it on the screen, but that is 20 degrees, and that is going to be 30 degrees. Okay, that is my free body diagram. I've identified all of the forces acting on it. I've written the net force. So now I'm going to use Newton's second law in that component form to think about what is happening here. What you want to do is separately consider what's happening in x and y. In x, I take my x component of tension 1, and notice that that's to the left, so that needs to be negative. I have my x component of tension 2, which is to the right, so that's positive. And since my object has a net force of 0, this must equal 0, the sum of these. Now I think about y. My y component of T1 and my y component of T2 are both positive, so these are added. And again, it might help to explicitly write this positive symbol there. And gravity goes down, so that's negative. Now, the next thing you would do in this case is actually think a little bit about the trig and the triangles to then break this up into sines and cosines of your different angles, and you would then have two equations with two unknowns where that is your individual tensions, and from that you would be able to relate that to your gravitational force. So I'm not going to do out the full math, but again, this step of going from your situation, using the equilibrium model to generate your free body diagram, and then breaking it up into components is very important and what I want to stress right now. So now I want to pose a question to you for a little bit of practice, and then I'll do it out. Is here's a free body diagram. I'm not going to be worried about telling you what the actual situation is, but the question is this in equilibrium? And the one thing that I want to clarify is that we have the x component of this force, right, that's equal to the 4 newtons, and then we have the y component of that force as well, equal to the 3 newtons. So it's explicitly given you the two components, and you have 3 forces total. So just for some simplicity, we can call this F1, F2, and F3. So go ahead, pause the video, take a second, and ask, is this in equilibrium or not? I'm not telling you what the motion is, but by having a complete free body diagram, you should be able to tell me if it is in equilibrium and therefore if it is accelerating. Okay, so to figure this out, you need to think about this in one of two ways. First is that you could actually just do the vector math. So if I draw out F2 and then I move it over to say F1 plus F2, I then need to draw out F3, and then I again move that over, I see that that doesn't bring me back to the origin. So just doing this graphically certainly does not seem to actually give me something that sums to 0. So the other thing that we can do is to actually do it out numerically. So if I want to first think about one component at a time, and I'm going to take fx. So this is going to be the x component of f1 plus the f component of f2 plus the f component of f3. And now note that when I write this out, some of these are going to be 0, and that's okay. It's absolutely okay to write something down and later plug in 0 for it. What you don't want to do is not write it down in the first place and then get it wrong because you didn't realize there was something to plug in. So the x component of f1 is positive 2 newtons. The x component of f2 is 0. The x component of f3 is negative 4 newtons. In this case, I hadn't worried about the signs up here, so I need to worry about the signs down here. So this is minus 4 newtons. Well, you immediately see that this is equal to negative 2 newtons, so therefore this can't be an equilibrium. So let's go ahead and also do it in y. And now we are going to skip that initial step, and I see that my F1 is 0 in y, my F2 is negative 3 newtons in y, and F3 is positive 3 newtons in y. This actually does work out to 0, but that doesn't mean it's an equilibrium in y. That doesn't make any sense to say. It is either completely an equilibrium or not at all an equilibrium. So in this case, we would say that the acceleration of our object is not related to the y at all. That's good. That this is actually going to be equal to negative 2 newtons divided by whatever the mass of my object is in the x hat direction. And notice in this case, the negative tells you that it's moving to the left in the x direction. So we have an acceleration, therefore it is not an equilibrium. The answer is no. So when you have numbers, you can do this out. The flip side is that if you didn't know one of these values and it was an equilibrium, you could have used this approach to find that missing value.